Hello everyone, my name is Matthew Fleming, and today we're going to be going over the information from our previous video and the experimental data that we found, and we're going to find how it relates with the Antoine equation. We're actually going to do this by superimposing the Antoine equation on top of the experimental data we found, and just to give us a better visualization of how they relate to each other. And so to do this, we're going to do a couple of things. First of all, we're going to get our original experimental data here first, and then we're going to superimpose the Antoine equation on top of this, and hopefully if our data and the Antoine equation is done correctly, then we should see that these data points line up directly on the Antoine equation curve. And so to do this, we're going to import some Python libraries. We're going to import JAX, NumPy, and that's going to allow us to take numerical derivatives of this data. We're also going to import requests to allow us to draw data and information from HTML code. And we're going to import Plotly, and that's just going to allow us to make pretty plots. And then we're going to import this minimize feature here so we can minimize a function later on. And then finally, we will import JAX, or we'll configure JAX so that we can use 32 bits or 64 bits instead of 32 bits, and that's going to allow us to store with double the precision, and just make our calculations more accurate. It's not too important for a simple calculation like this, but it can be very important later on. So the original URL is just this Dortmund data bank website right here, and it's just the vapor pressure of water. And so at varying temperatures and its varying vapor pressures. So of course we have this data in this table, and we have the temperatures in Kelvin and the pressures in kilopascals. We actually want this in pascals, so we'll change it later. But this data is what we're working with. And so that's the original URL. And then the URL we're going to use for this is actually just the HTML code for that page. And of course you can see some of the information from that data, or that data from that table right here. So that's the URL we're working with. We can take any variable, we're going to call it DDB for the Dortmund data bank. We're going to set that equal to request.getURL.content. And so that's just going to take this HTML code right here, and the information and the data from this code is just going to be called DDB, and it's going to be stored as strings. And we're going to make a tree, and we're just making a tree of all of this right in here. Then we want the temperature and the pressure strings, and so we're going to set that we're going to draw the temperature strings and the pressure strings from the XPath of this table. And we went over how we can use the XPath to find information in the previous video. And so we can see that in the table data 1 is equal to all the temperatures, and then the table data 2 is equal to all the pressures. And so we're literally just taking this right here, and we're calling these the temperature strings. And then this right here is the pressure strings. And then we're going to set a variable called data, and we are going to make an array, and it's just going to be the temperature strings in the first column and the pressure strings in the second column. And we're going to save all these strings actually as float64, so it's going to instead change them from strings to numerical values, and it's going to be stored on 64 bits rather than 32, so it's going to allow us to have that double precision. That is not too important for this one, but again, it can be very important in more complicated calculations. Now we're going to set T for temperature, and we're going to set it equal to the data in the first column, all the data in that first column of the data array. And so temperature is just, again, we're setting temperature equal to this column right here, or these values right here. And then we're going to set the log of pressure equal to the log base 10 of the second column of this array right here. And so this is all in kilopascals, as we can see right here. And we want that in pascals. So we're going to multiply each one of these data points in this array by 1,000 to get it from kilopascals to pascals. And then we're going to take the log base 10 of those, and that will give us the log base 10 of the pressure, and it's going to be in pascals. And so that's our second variable right here. Log P is just the log base 10 of pascals for this column right here. Now we're just going to make a graph. We're going to graph these, and the x values are, the x-axis is going to be the temperatures in Kelvin, and the y-axis will be the log base 10 of the pressure. That's in pascals. And we want these in markers because this is all experimental data that has been found, and we don't want to use a trend line because a trend line would just ruin the reason why we have experimental data. Right? Experimental data is found to give us exact x and y values, so we want all these data points in markers. We don't want a trend line. And so that's all this cell is doing right here. And this is our beautiful graph. Now we're going to define a model, and this model is just going to be the Antoine equation. And so we're going to take in inputs A, B, C, and then the temperature, and we're going to return A minus B over C plus T, and that's just the Antoine equation. We're going to set a couple guesses for A, B, and C, and this is going to then be varied here in a second. And then we're going to have this array or this list, and it's going to be it's going to have the A guess, the B guess, and the C guess within it. Now we're going to make a function, and we're going to calculate the square error of A, B, and C. And so what we're going to do is actually take in arguments x, temperature, and log base 10 of the pressure. And x is just this list right here, and we're going to take this model P, and we're going to set it equal to this model of x, the first value of x, which is this A guess, and then the second and the third, so the B guess and the C guess, and we're also going to have the temperature in there as well. And we're going to mark the error as being equal to the sum of the guesses as well as the temperature subtracted by the log base 10 of the pressure, which again is the y values of this graph, or all of these values, the log base 10 of these values times 1,000. And we're going to square that. And so that's going to give us our error. And now we're going to call the result as we're going to set a variable called result here, and it's just going to be the minimization of this error. And so we're going to take in arguments, temperature, and log base 10 of pressure, and we're going to make a tolerance of 1 times 10 to the negative 10, so a very small tolerance. Now we're going to have the computer just minimize the error, essentially, and it's going to give us accurate A, B, and C values for the vapor pressure of water according to the Antoine equation. So we can just go ahead and run this cell. Actually, we want the result, and the result here is going to give us the array, and it's going to be our A, B, and C values here. So we have A is 10.2, we guessed 10, so that's good. And then our B and C values vary a little bit from our initial guesses, but these are our A, B, and C values for the vapor pressure of water in the Antoine equation. So now that we have these values for the Antoine equation of water, now we want to superimpose that Antoine equation according to the values we found in our model on top of the experimental data we found from the Dortmund Databank website. And so to do this, we're just going to set a new variable, we can call it T model, and we're just going to make a list, and it's going to be from the first to the last temperature values, and then we're going to have 100 increments in between. And then we have a total of 100 different values in that list. And then we're going to add to that scatter plot, we're going to have the x values are going to be, again, T model, and then the y values are going to be the combination of the result, which is this array right here with our A, B, and C values, and the T model here. And we're going to make this as, we're going to use the trend lines for this because, again, we're finding the Antoine equation's prediction for water, for the vapor pressure of water. And so this is going to be able to find us temperature and a pressure for every temperature. And because it's an equation, it's going to be valid for any temperature we can think of. So we want a trend line to show us how, the trend of the Antoine equation rather than experimental data, or rather than data points, which will be used for experimental data. So we're going to use the mode for this for this as lines, and then we're going to just name it the Antoine equation right here. And as you can see, the Antoine equation actually lines up right with the experimental data, which just goes on to, which further implies that our experimental data is accurate, and also implies that our model here is fairly accurate. And so that's all it is. That's how you fit the parameters of the Antoine equation towards the experimental data that we found from the Dortmund data bank.